Hello, hi, how are you? How's everything? I hope everything is going well with you and you're having fun with your families in these lockdown days. So, I'm going to continue talking about the Laplace, and today I'm going to just tell you quickly about the integration in Laplace domain. You all remember from the properties that the derivative in Laplace domain was really easy. You're just multiplying the function by s. Integration is also very easy. If you want to find the Laplacian of the integral of f of t dt in s domain, you just divide the f of s by s. That means that you don't need to do the integration. You just find the Laplacian of f of t divided by s. So this way you have found the Laplacian of the integral. It's really cool. I had promised you in the beginning that there is a reason that we're going over this hassle to learn the Laplace transform, because it makes our lives easier in many aspects. One of the aspects is this integration. So let's see how this thing can make our lives easier. As you saw in the formulation over there that I was showing you, the Laplacian of the integration of f of t is f of s over s plus the integration of minus infinity to 0 negative of f of t dt over s, where let's call this thing the initial value somehow. Okay, so let me explain for you more in an example. Imagine we have this integral equation 16 f of q dq plus d of dt f of t equals 2ut. So we want to solve this equation. How to do that? We can take a Laplacian from both sides. Let's take the Laplace transform from the left hand side and from the right hand side, which is just 2ut. So the Laplacian of the integration is what? It's just dividing the Laplacian of the f of t over s. So the Laplacian of f of t is f of s, capital F of s. So 16 integral f of q dq is going to be 16 f of s over s. Plus, we have the derivative. Derivative was multiplication by s, right? So it says s f of s minus f0 negative. This one was also in the table. This is the initial value, this f0 negative. So I'll tell you a lot about it later on, because this initial value could be important when we use Laplace in circuit analysis, and especially in the circuits that there are capacitors and inductors involved, because those components can store energy, and the energy stored in them at the beginning of the operation of a circuit can be counted as an initial value. So this thing will be used there. For now, you imagine it's a constant. Okay, it's a constant. So now I wanna take a common factor from f of s. It will be 16 over s plus s minus this constant equals 2 over s, right? Then it means that f of s times 16 plus s squared over s equals 2 over s plus f0 negative. So I'm going to divide both sides of this equation by this bracket. So this side, of course, only f of s will be left. The other side will be 2 over, because this s, when we divide it, this is cancels. This is going to be 2 over 16 plus s squared plus s f0 negative over 16 plus s squared. So I guess you now, after all this practice that you did on partial fraction and stuff, you know how to take this in back to time domain. So this piece will be a sine, right? Omega over a square plus omega square. So half sine of 4t ut plus, I told you, just keep this as it is. It's a constant. Sometimes actually a lot of times it's zero. A lot of times this initial condition is zero, but not all the time. Depends on your circuit or the signal that you are analyzing. But right now we just keep it as a constant, f0 negative. So it's going to be this thing, s over s square plus omega square is just a cosine. And the coefficient will be just f0 negative. So the answer to this integral equation that you had is simply this. Half sine of 4t ut plus f of 0 negative cosine of 4t ut. Could you ever imagine that you can solve this second order differential equation in 3 lines? Look, basically 1 line, 2 lines, 3 lines. As simple. This is one of the important merits of the Laplace transform. It will make our lives much easier when it comes to the differential equation. Now, let's try this one. You want to find the Laplace transform of the signal f of t sketched in the figure below using the integration property. So you want to find the Laplace transform of f of t using integration. So note that the triangular waveform f of t is the integral of the square wave g of t. Okay. So how to do it? Let's write the description of gt. gt, as you can see, is simply ut minus 2. Look, it's ut. Then at capital T, we have to deduct 2 ut from that, right? So minus 2u at t minus capital T. Then here at 2t, we have to add another u plus u at t minus 2 capital T. So this is your gt. Now, what is the Laplacian of gt? What is the Laplacian of gt? Is going to be Laplacian of ut is 1 over s. This is going to be 2 e to the power of minus st over s. This is going to be e to the power of minus 2 st over s. So I can take a common factor from 1 over s. It's going to be 1 over s. 1 minus 2 e to the power of minus st plus e to the power of minus 2 st. Now, the Laplacian of the f of t, okay, look, imagine this is the integral of this one, right? So the Laplacian of this one is basically the Laplacian of the integral of this one. So the Laplacian of f of t is actually the Laplacian of the integral of gt or gq dq. But how do we deal with the integral in the s domain? Just divide it by s, simple as that. So I have to divide it by s. Do I have the Laplacian of the gt? Yes, this is the Laplacian of gt. So I divide it by s. So the answer will be 1 over s square times 1 minus 2 e to the power of minus st plus e to the power of minus 2 st. So now I want you to try to solve this example. Look, this circuit is a simple linear circuit including 1 resistor, 1 inductor and 1 capacitor. We have a resistor of 4 ohm, an inductor of 1 Henry and a capacitor of 0.25 farad. We know that Vin is delta T, and we know that IL0 negative is 1 amp. It's the initial condition. And VC0 negative is minus 2. What are these two? Let me remind you of something. Do you remember this F0 negative in this equation that we had before? This is that initial condition. So over there, this value is given to you. You remember I was telling you when there are circuits including capacitors and inductors, they do store some energy inside them. That energy, it shows itself in the beginning of the operation of the circuit as some initial value. This is the initial value. So in this circuit, the initial value stored in the inductor in the format of current is 1 amps, i.e. L0 negative is 1 amp, VC0 negative is minus 2 volts. So can you try to solve this yourself? Also, I'm just giving you a hint. The solution of this is in lecture note 18. I would like you to go over it because I want to explain something for you later. With the information that you have, you must be able to solve this problem. Okay, you want to find the current IT. Shouldn't be a big deal at all, right? And of course, use the Laplace transform to do that. I don't want you to solve a second order differential equation. But after you solved it, I will try to show you some tips and tricks that how to deal with inductors and capacitors in the presence of the initial condition. So good luck, have fun, take care, and I'll see you soon. Bye bye.